equation.
Yeah, thank you. And I thank you also, Alexei, for organizing and to allow me to make this presentation here. And to be honest, I was not very comfortable when this meeting started because I was thinking that I will meet more colleagues here that working with soils and things like that. And because I am an agronomist, I have problems with calculations. And my talk here has a different aspect because I came here for help. I will not show results. I came here with a question. And yeah, because I was interested because we were working with pores, and then I see the title of the workshop, and I see the name of Van Genushen. Oh, this is interesting. But now I thank also my colleague from, I think it's from Saudi Arabia, that bring me in my word before my talk. What I will talk here, it's about the importance to estimate soil porosity. We are talking about pores in the last 3 days, and but we from Embrapa we study pores with a specific task. That is, in the pores we store water, and we have fluxes of water that govern growing of plants or discharge of water, movement of water in soils. And estimating porosity is a task for us. And we basically use it one indirectly way to estimate it, based on capillarity equation. And I will show this, how we do this, and I will show how our laboratory methods and the last speaker talked briefly about pedotransfer equations. That was my question here. If we can do a pedotransfer equation to estimate soil pores, a specific soil pores. And we have a lot of pedotransfer in the literature, but mostly are statistical pedotransfer. What I am looking for is for a physical-based pedotransfer equation for pore size. Yeah, what's the importance for us in agronomic view to study porosity? Because we use this as indicator of compaction. When we have this agricultural fields with these heavy machines and implements, we change the pore size distribution and we make some compaction. We reduce the total porosity in the most part of the case. This is a very serious problems because we reduce infiltration and we have erosion and things like that. And we need the porosity to estimate it available water, what we normally calculate it between the soil moisture in 2 points that we call the moisture in field capacity and the moisture in what we call it the wilting point. Permanent wilting point, and that's my specific task here about this point here. And the importance is this. The insurance for farmers is based in this simple equation here. They give you money, or they give you the insurance based in the available water of your soil and the thickness of your soil. And then they determine, okay, you can have insurance if you have this soil and you plant corn until 15 October. And to modeling soil, water, and air fluxes has showed the last speaker. Yeah. Nowadays, the state of art to determine porosity in soil samples is tomography, but this is quite expensive. and you cannot deal with many samples with this. And what we, the most part of the world is still using is to estimate it, water holding capacity at different pressures, and indirectly estimate the porosity. Yeah, this is the rise of a capillary, water in a capillary that we use it to estimate the pores in soils. And most part of these parameters are quite fixed, and this can be reduced, but this H here is the water pressure head expressed as equivalent height in a capillary tube. And for the permanent wilting point that I will explain a little bit better later, it's 150 meters of pressures. We pressured we saturated our soil sample, and then we pressure with this, and we measured how many water is still there. And if you do this, and you calculate it, what we call the equivalent soil pore radius that remains filled with water after we pressure with this here, it's this here. To talk about fine pores and small or coarse pores, it's changed for forum to forum. In the first day, we have a talk here where someone was measuring nanopores. We are in another scale here. For us, here is very fine pores. And the water that remain after I apply this in a soil sample, that's what they call it permanent wilting point, because this water we consider not available to plants. It's held with so many energy. This is a funny history because it came from an experiment with dwarf sunflowers. Of course, that is not valid for every plant. Cactus can collect water in this. Lettuce cannot collect this in 1,000. But this is a fixed point. I think the name nowadays make more troubles than solutions. Most part of the people use it this point to fit these equations that allow to model water fluxes. The way that we do this, we collected samples, what we call it undisturbed. We insert these metal cylinders in soil and cut here and cut below, and we have, this is for low pressure when the structure of the soil is more important, and we also collected disturbed soil when we have these high pressures. And then to keep the structure and all this work doesn't make so many sense anymore. And this is what we call tension tables. We put the samples here, and we apply a difference of hydraulic continuity here, and we can measure the water holding capacity in low pressures. Then we put in this what is called the Richard chambers, that was in an airline with pressure here, and then we can control here the pressure, and then after equilibrium we weight the sample again, and then we have in this pressure how many water is held in the soil. This Richard chambers has a ceramic plate where we put the soil samples here and pressure. And then they have some drains here that we control what we call it equilibrium, but this equilibrium is between commas because this is not a really equilibrium. And most part of the results, when we have these pressures, the volumetric water content range, of course that I have some exceptions here, But this is typical for very sandy soil. This is for clayey soils. This is another technology that's starting to become standard. This is for dew pointed, but we just started to measure. But we have many unsures using this equipment until now. This you cannot control the pressure. You have a sample, you put there, they will tell you what is the soil metric potential, and then you wait, and then you have a point. But my colleagues, they are used to 1,500. If I give them 1,600, they are not happy. And then I need to make 3 or 4 points and adjust a line and give them. Okay, we have a method why we are not happy, because this is time consuming. It takes weeks to have this equilibrium. This is expensive. To have this pressure that for many of you maybe doesn't seem to see very high, but the normal compressors is only 1,000 or 700. And to have this, you need 2,000 compressor. It is quite expensive and not easy to buy. We have a large demand of this. And then we cannot do like for tomography, because many people are interested in this. And reliability, because the equilibrium point is a not easy decision. Okay, stop the measurement. Let's see how many water is held there. Therefore, many people are looking for these pedal transfer functions. What's pedal transfer? Are predictive functions of certain soil properties. Here is water hold capacity or pore size when the pressure is 1,500 kilopascal, using data from soil surveys. Many people use it, and now in hydros, that was mentioned in the talk before my talk, they have a neural network pedal transfer that you can estimate some hydraulic parameter using hierarchical information. If you know only the texture class of your soil, clayey soil, they will give you some. If you know, no, I know that it's clay, and I know that it's 6% clay, 20% sand, and 20% silt. They will improve it. And if you know, okay, I know that the bulk density is 1.1. And we have many of these pedal transfers. And why I am not happy with it, these pedal transfers. I will briefly show a little bit about soil in the world. Of course, that this map can change the color with the legend here. This is a legend for classes of soil or type of soils that concatenated many information. If okay, here in Brazil we have oxo soils. This word probably for many of you doesn't mean anything, but for my colleagues that work with this, it means a lot of things. And here in Europe I have molly soils in Rusland, and this is one kind of, and this soil, this same color have many similarities, not all similarities for water holding capacity, but have many similarities. And here is from Brazil, a map organized by Embrapa and other colleagues, and then we can see some types of soil that is distributed in Brazil. And here is some collection of pedal transfer papers. Some are from these years, and the most part of this paper using statistical approaches. Very simple ones, linear fitting. Or more complicated, their nearest neighbor, that's things that I don't know exactly what they are doing, but they are doing this. And also here, these three here are from Brazil. This Hoodnet and Tomazella, they work mainly in the Amazon. This is Eusébio. They work in the Brazilian savannah, in the center of Brazil. And this team here in northeastern of Brazil. And in Brazil, we have also pedal transfer for Santa Catarina. We have a pedal transfer for São Paulo. And soil properties don't have passport. Soil properties, the limitical borders cannot stay in the title of pedal transfer functions. Maybe the class of the soil, but not the region. And of course, that people that have working with database and have working with this fitting equation in database, it will change with your database if it's not very robust equation. And yeah, only some example of these pedal transfer functions. Yeah, the most part of the pedal transfer function to estimate it, this point here that we can estimate the pore size is based in bulk density and clay content, silty clay content, and the textured class. Some use it sodium, some other use it yeah, specific surface. I have found only one that uses this. And people work with very specific database. And some people are using this physically based estimation. But the paper that I have found using this word, physically based, it based in texture. What I am looking for a pedal transfer function that is more global, more general, came from one work that I did many years ago. I have this situation here. I was using a technique that now it's became standard to evaluate soil moisture, that is reflectometry in the time domain. This is TDRs to estimate volumetric soil water content. This technique has one considered universal equation, that is top equation. That is one equation like this here. When I have my data from the Amazon and I put the top equation here, top equation was subestimated. And then, okay, I need to calibrate my TDR. And then I started with this, fitting these equations. And it's a lot of work, and then you see for how the best fit, and then you see for this parameter that is many, many books I read about how to choose the best equation. And then I have found some papers that is physically based equation, because when I use TDR, what I am measuring is the electric constant of the medium. And the soil is a mix of air, water, and the mineral substance. And every of these have different electric constant. And the difference is big because air is around 1. The mineral soils is around 3 to 5. And water is 8 to 1. And then water governs the electric constant of soil. But 8 to 1 is the electric constant of free water. The bound water is not 8 to 1 because the water that is covering the surface of some layers, they behave like ice. They cannot rotate it because they are a little bit strong. And if you can divide your water, what is free water? What is bound water? That's a problem that happens especially in clay soils. You can use it, a physical equation to estimate volumetric water constant, measuring geoelectric constant of the mix of soil, water, and air. The problem was, okay, we have the equation, but how to estimate the bound water? Then I have found this equation. The bound water can estimate it by this equation where the first term here is the number of molecular layers of tightly bound water. And the second one is the thickness of one molecular water layer. S is the specific surface of the soil, and and the last one is the bulk density. And then I can estimate it, what was the bound water. And then I divided my water, bound water, free water. And then I have equation that can be used, because many people ask me, oh, I am using TDR. I need to calibrate it. Okay, do this boring work here. A lot of work only to have the calibration, then you start doing your task. Because the other parameters are very common and very easy. And then I got interested, okay, physical-based equations are more robust, and are more, I can widespread if they are consistent. And then my question is, for you that are Porous specialists, can we make some concern or some approach to see, okay, what was the properties that hold the water in a pressure that 1,500 kilopascal. When I have this, I have very small pores. Pores that we can estimate that is low, and then the radius is lower than 1 micron. And do you believe that we can found a physical-based equation to estimate at this point? That is, I think, something strange for a talk, but this is a question, not a conclusion. Yeah, thank you very much.
Thank you, Wenceslao. Question, comments, answer the question.